Professor Carlos Frank of Durham University states, "Yeah, I've spent my whole life developing a particular theory of the universe, and now the theory is being challenged. I welcome that because that's how we move forward, that's how we make progress in science." The James Webb Space Telescope is overturning much of what has been considered truth in cosmology for the past 100 years. A new deep image shows that we have made mistakes. The telescope, which was supposed to show us the first stars of the universe, is becoming a killer of the established worldview and may bring us a whole new science. Not all researchers are fearful of the new facts. Many scientists welcome the developments because it has long been clear that something was wrong with our old models. The discrepancy in the measurement of the expansion rate of the universe alone should have shaken researchers awake years ago. Instead of interpreting the warnings correctly, they clung to old theories. The cosmic microwave background, CMB, considered the oldest light in the universe, was created around 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to form stable hydrogen atoms. Researchers call this transition the recombination, which made the universe permeable to light. The CMB was first discovered in 1964 by American physicists Arno Penzias and Robert Wilson while they were working on a new type of antenna technology. This discovery was long regarded as one of the strongest pieces of evidence for the Big Bang theory, earning Penzias and Wilson a Nobel Prize and a prominent place in the history of astrophysics. The CMB likely offers a snapshot of the young universe, with tiny temperature fluctuations providing important information about the conditions shortly after the Big Bang. Scientists use the CMB as an imprint of the basic metrics of the material cosmos to measure the expansion rate of the universe, among other things. The astronomer Edwin Hubble had already calculated this in the late 1920s, discovering that distant galaxies move away from us in all directions and that their speed is proportional to their distance. Today, these observations are known as Hubble's law or the Hubble constant. Hubble did not have the advanced measuring techniques available decades later when the CMB was discovered, which led to a recalculated expansion rate significantly lower than Hubble's original figure. Later, scientists recalculated the rate again using type Ia supernovae as standard candles, providing stable light that could be used as reliable measuring points. Measurements within the CMB yielded an expansion rate of about 67 kilometers per second per megaparsec, while measurements using supernovae yielded about 74 kilometers per second per megaparsec. What does this difference in determining the expansion rate of the universe really tell us? Did you know that this discrepancy has been known since the 1990s? Since then, researchers have known or suspected that something might be wrong with the assessment of the CMB, the measurement methods, or the idea of the universe's expansion. The discrepancy between the various measured values of the expansion rate is known in science as the Hubble tension. The implications of this tension are significant, suggesting that profound aspects of our understanding of the universe might be flawed. For a long time, researchers were at a standstill. Since the James Webb Space Telescope went into service, it has provided scientists with surprising data that may now shed light on the problem of the expansion rate of the universe. Galaxies so old and mature that their formation must theoretically precede the Big Bang are overturning old astrophysics. Researchers no longer talk about discrepancies or measurement differences. They speak of the biggest crisis in modern astronomy. Not only could the expansion rate be wrong, but the whole idea of expansion or the Big Bang itself is being questioned. Webb's observations provide evidence of a universe very different from what we have long thought. The Hubble tension was the first warning, and researchers who still believe in old models now face a problem. Do we really know nothing about the universe? Many scientists stand on the ruins of their life's work, looking into space with confusion, no longer understanding what they see. In light of the crisis in science, we must ask ourselves what we truly know about the universe. To answer this, we need to understand how science operates. Theoretical scientists use a complex web of mathematical models, empirical data, and deductive reasoning to draw conclusions from the general to the specific. Their knowledge derives from a combination of observed phenomena, experimental results, and theoretical analyses. The term theory alone indicates that these are hypotheses and ideas, not absolute truths. The only practical knowledge we have are the images telescopes provide, the sound waves and radiation captured with radio telescopes, and the latest data from neutrino observatories or gravitational wave detectors. With the James Webb Space Telescope, we now have an instrument that can break down the oldest light into individual frequencies and analyze it in unprecedented ways. Webb can show us the predominant elements in galaxies over 13 billion years ago, how much mass they contain, and how many stars they have. It can also reconstruct the shape and direction of a galaxy's movement. However, Webb can also have weaknesses. For instance, it cannot always determine with certainty whether we are seeing galaxies or black holes with huge accretion disks that shine as brightly as a galaxy. We must face the fact that our science has long accepted too many eventualities as truths and disregarded alternative explanations. Research has long been certain of its models, but the latest findings from the James Webb Space Telescope are crucial clues to replace theories with new truths, as has happened many times in science. Scientists are currently awaiting new discoveries. They are too astonishing, and many researchers struggle to come up with new explanations. The new findings shake the foundations of our physics. Today's teachings of physics are still largely based on Isaac Newton's research from the 17th century. His laws of motion and gravity were the foundation of our physical understanding of the real world and the universe for centuries. Newton's laws explain the movements of objects under everyday conditions and work well on Earth. However, in space, his ideas needed extension, a task accomplished by Albert Einstein at the beginning of the 20th century. Einstein's special theory of relativity, published in 1905, transformed our understanding of space and time, proving that they are relative to each other and depend on the observer's movement. His general theory of relativity, published in 1915, extended this concept with mathematical proofs of gravitational phenomena based on the curvature of spacetime by masses like stars or galaxies. Einstein's laws and ideas were revolutionary, but he also knew their limits. He knew his theories would never fully describe the universe and dreamed of finding a world formula, which he did not achieve. No other physicist has succeeded in this endeavor to this day. Where is the flaw? Wouldn't it be interesting to know? Michio Kaku, a popular astrophysicist from the USA, said in an interview that solving this problem would surely win a Nobel Prize. Let's explore the facts. Scientists might have overlooked possible misinterpretations or whether our models are to blame. Dark matter and dark energy are at the top of the list of suspects for the real cause of the cosmological crisis. Our current models of the universe include concepts that dark matter and dark energy make up about 95% of the universe. However, neither has been directly observed, and their real nature has never been proven. They might not exist at all, necessitating different explanations for the universe's expansion and the dynamics in galaxies. Or they might have properties we do not yet understand. One idea is that the physical properties of dark matter and dark energy have changed over time, possibly indicating some kind of intelligence. Gravity is another phenomenon to be tested. This force, supposedly responsible for attraction through mass or curvature in spacetime, has not yet been proven. The ideas of spacetime curvature largely originate from Einstein and have been confirmed many times. However, we cannot rule out the possibility that gravity has different properties than we thought or that another effect causes the gravitational pull between objects. Over the decades, several values have been established in cosmology and astrophysics as constants. The exploration of the cosmos has always been a journey marked by our relentless quest for understanding and discovery. From ancient civilizations observing the stars to modern-day space telescopes probing the depths of the universe, each advancement in technology and theory has unveiled new mysteries while challenging established beliefs. In the realm of cosmology, the James Webb Space Telescope, JWST, stands as a beacon of our scientific progress, poised to revolutionize our understanding of the universe's origins and evolution. Launched with unprecedented capabilities, JWST represents a leap forward in observational astronomy, capable of peering deeper into space and time than ever before. One of the primary objectives of JWST is to study the cosmic microwave background, CMB, with greater precision. The CMB, often referred to as the afterglow of the Big Bang, provides a snapshot of the universe as it existed merely 380,000 years after its birth. This relic radiation carries valuable information about the universe's initial conditions, including its temperature fluctuations, which are crucial for understanding the formation of galaxies and large-scale structures. The discrepancy in the measured values of the Hubble constant, known as the Hubble tension, has been a persistent issue in cosmology. While CMB measurements suggest a lower expansion rate of the universe, observations using Type Ia supernovae and other cosmological probes yield a higher value. This tension implies that our current models may be incomplete or that there are fundamental aspects of the universe's expansion dynamics that we have yet to grasp. Beyond the Hubble tension, JWST has the potential to shed light on other fundamental questions, such as the nature of dark matter and dark energy. These elusive components are hypothesized to constitute the majority of the universe's mass-energy content, yet their existence remains inferred indirectly through gravitational effects rather than directly observed. JWST's ability to study the distribution and behavior of galaxies and galaxy clusters may provide indirect evidence to unravel the mysteries surrounding these enigmatic entities. Furthermore, JWST's observations could challenge the current paradigm of cosmology itself. The discovery of mature, well-formed galaxies at epochs closer to the Big Bang than previously thought suggests that our understanding of galaxy formation and evolution might require significant revision. These observations might indicate that the processes governing the early universe are more complex than our existing models can accommodate. In addition to its cosmological endeavors, JWST's capabilities extend to the study of exoplanets and their atmospheres. By analyzing the light passing through exoplanet atmospheres during transits, JWST can identify the chemical composition and potential habitability of these distant worlds. This aspect of JWST's mission aligns with the broader quest to answer one of humanity's most profound questions. Are we alone in the universe? In conclusion, the James Webb Space Telescope is poised to redefine our understanding of the cosmos. Its advanced instruments and unparalleled observational capabilities promise to address long-standing cosmological puzzles, challenge established theories, and potentially lead to new scientific paradigms. As JWST continues to collect data and unveil the universe's hidden secrets, we stand on the precipice of a new era in astronomy, where the answers to our deepest questions about the origins and nature of the universe may finally come into focus.